Welcome, everyone. It looks like we have a large crowd here, and it's a great feeling because astrophysics is exciting. So it's great to see all of you. We are holding it in this small room because the bigger room, Philips, is taken by a conference. And they asked for my approval. I said yes, because it's a very interesting conference about clusters of galaxies. So we were generous and gave them the space, and that's why we are crammed in this small space. But it's okay, we get to know each other better this way. And it's only for this week. So next week we are starting over there, and so I hope to see all of you there. As everyone knows, this is the ITC lunch, and we hold it every Thursday, 12:30 to 1:30. We have a lot of new people that I will introduce in a second. But first, I wanted to thank Eric Keto for funding this forum. Where is Eric? Over there. So Eric is not an external donor. He's an internal donor. He's a member of the ITC for many years and was generous to provide us with the funding for this forum, and we are grateful for that. There is also the Keto Prize for the best PhD thesis in theoretical astrophysics given every year, and usually it's at the end of the year, so you will hear more about it. Some of the students here may wish to produce good papers in order to be eligible. First, I wanted to extend a warm welcome to the new members of the ITC, and let me mention who they are, and please raise your hand so everyone would know who you are. The first is Monica Gallegos Garcia. Here she is. And she's an ITC fellow. Oliver Zier, that spoke today, yes. Again, ITC fellow. Anya Nugent, a postdoc with Ashley. Right? Yiz Dong, right here, again, a postdoc with Ashley Villar. Christian Garcia Quintero. He here?
He may not be here today.
Oh, okay, just arriving, Hubble Fellow. We're very happy we have the Hubble Fellow. A more senior person, Liam Connor, right here, is a new junior faculty at the astronomy department at Harvard, and played soccer very well, I can say. You scored the last goal for the faculty. Yeah. So we are very happy, not just scientifically, that you joined us. As I mentioned, after we have an annual soccer match between the students and the faculty, I mentioned that we are happy to recruit members of the student teams to the faculty team as well, in future years. And then we have two sabbatical, another postdoc that I should have mentioned, Danielle Frosty. Is Danielle behind me? Okay, it's great to see you, Danielle. So you're joining us from not very far.
No.
Right, from MIT.
Yeah.
Yes. You gave an ITC presentation. Yes.
Last fall, yeah.
Yeah, exactly. Okay, and we have two sabbatical visitors, and I should say only two because we had a lot of applicants, and because of space limitations, the director's office, the CFA, allows us to get a limited number. And so the ones that joined us are Ralph Klessen. Where is Ralph here? No? Maybe right. Oh, no, it's a different Ralph. This one is a senior faculty from the other one is a teaching fellow in my class.
Almost the same.
The same first name, yeah. Merav Ofer, is she here? No, she's from Boston University and will join us as a Radcliffe fellow. And then we have new grad students. Ron Grong Liu, not here. Tintin Nugent, not here. Anya Phillips. Oh, right here. Yeah, wonderful. Sophia Grace Ridolfo. Oh, welcome. Anna Rose Tartaglia. Is Anna here? No. And Guijia Zhu, previously a Harvard undergrad, but I don't see here. And then I should mention that we will have the ITC reception 2 weeks from now on Saturday. So that's the 28th. Actually, it's 3 weeks. 3 weeks, yeah, 3 weeks from now. And everyone is invited. It's between noon and 3 p.m. and there will be transportation, buses taking off from this area outside the CFA, right in the parking lot. And it's usually a very fun event, excellent food, so everyone is welcome. If the weather is not nice, we will gather indoors. So don't worry about it, just come irrespective of the weather. Yes?
A couple of other people to introduce who weren't on your list.
Oh, okay.
So Peng Wu Sun sitting across from you.
Oh.
The new postdoc in my group. James Trussler, new postdocs. Tiger Shao, who's visiting for the year from Johns Hopkins.
Oh, okay. Welcome. Thank you, Daniel. Okay, so let's start with lunch. We'll hear from our speaker today. We had an excellent ITC colloquium by Oliver Zier, who will tell us about formation of low metallicity stars in THESAN-ZOOM.
Great. Yeah, thanks a lot. Today I talk about the formation of low metallicity stars, or more specifically POP3 stars in the THESAN-ZOOM simulation. This work is still not even hot in the press. It's still ongoing analysis. So it's very new results. And I talked together for the THESAN-ZOOM collaboration, so I don't do those simulations alone. And very short introduction, what are POP3 stars? So here, a short summary of the evolution of the universe. We have initially the Big Bang, then afterwards we have at some point recombination. We have a neutral intergalactic medium afterwards. Then the first perturbations start to grow, and we form the first stars around redshift 30. This then continues, then we get first galaxies and later redshift. Then those galaxy stars start to form ionizing radiation, we get ionizing bubbles, and then at some point we get fully ionized IgM and modern galaxy formation. And so what I will today focus on are metal-free stars. So the first stars which formed from crystalline gas, so just helium, hydrogen, and some very small forms of lithium. And doing they assume to like around redshift 30, and then later redshift under redshift 15 maybe, and then we form metal-rich stars. Those metal-free stars, they start to form the first halos, so mini halos, of the size 10 to the 6 and 8 solar mass. Because they don't have any metals, they cannot do metal and cooling, then they have to use molecular hydrogen to cool. And then this is only efficient up to like 100 Kelvin. So those first star forming regions were significantly hotter than modern molecular clouds. This is assumed to also lead to a different initial mass function, the more top-heavy IMF, so you get like more massive stars. You don't really form small stars. And because they are so massive, it's also very short-lived. But they are very important because they produce the first metals which then are used for the next generation of stars. And so why do we don't observe them anymore in the modern universe, or why do we don't observe them anymore? The reason is first because they form those metals that pollute the gas around them and they die. So the next generation of stars has metals. And additionally, there is Lyman-Werder radiation. So it's radiation which does not ionize hydrogen, like atomic hydrogen, but it can destroy molecular hydrogen. And so you start to build up like this radiation background. You can destroy those molecular hydrogen and you just cannot cool it anymore. And so the THESAN-ZOOM project, this consists of zoom-in simulations at the high redshift universe up to redshift 3. It consists of 14 galaxies selected from like a parent THESAN volume. It uses much higher resolution and a multi-phase ISM, so you really have like different phases. And additionally, it contains dust physics, it contains non-equilibrium chemistry, including molecular hydrogen, and 7 radiation bins. So not only ionizing photons for hydrogen and helium, but also Lyman-Werder radiation and additional bins. And the resolution I show here. So because we simulate halos from 10 to the 8 to 10 to the 13 solar mass, it differs between different simulations, but the best simulation we can achieve is around 140 solar mass in the gas phase. And even the more massive halos, we still have around 10 to the 4 solar mass. So we can really resolve also those very small 10 to the 6 to 10 to the 8 mini halos and really see how there's a structure in those halos. And here on the right side, I just showed an illustration, how you can really see like a multi-phase or very small things within the galaxy. The project itself was run by Raoul Kanan and then a lot of collaborators. And I talk today mostly about what I was doing. So there's just another illustration. On the left side, we have like large-scale THESAN simulation, like a large box. And then we take a small halo and zoom in and add this high-resolution multi-phase ISM model. So what I was doing is I was looking at redshift 3, so the final redshift of our simulation. I show here for 14 halos we were simulating, going from the top left, this most massive one, going to the right to less massive, and the lower one to the even less massive ones. And I check all of the stars which we can find, trace them back at what redshift they were actually born. And then on the y-axis, I show the metallicity of the stars. And well, as you would expect, the ones which are more to the left, well, like they are like younger stars, they're typically on average more metal rich. And if you have more massive halo, you also form more metal rich stars, just because you have more time, to produce metals before. But a very interesting thing is if we look like here, like at the smaller metallicity we find, it's around 10 to the minus 6 solar, or even lower solar metallicity. And it seems like we form those in all of the halos under redshift around 5, which is actually also in the simulation the end of realizations. And afterwards, we suddenly don't form them anymore, and we only form stars at like 10 to the minus 3 solar mass. And then I was checking the fraction of the different populations. So I defined just based on the metallicity of the stars. Above 1, if it's like metallicity more than 0.1 solar. Top 2, 0.1 to 10 to the minus 6 solar. And top 3, smaller than 10 to the minus 6 solar. Maybe important to mention, if we add, like at the beginning, we give all of the gas a very small metal fraction, which means all of the top 3 stars, or like I'll talk about, are actually stars which form from gas which is not enriched at all by any previous star formation. And here I show the fraction of the different populations on a total new stellar mass with a function of redshift again. And you can see at very high redshift, up to redshift like almost 30, you start to form those top 3 stars, those super metal poor stars. Then in more massive halos, at some point, top 2 star formation takes over because you're already a bit enriched. And then in the most massive ones, at some point, you form top 1 stars, so very metal rich stars. And like the smaller the halo becomes, the later this transition happens. In the very small halos, you actually still start to form, or top 3 star formation might still dominate up to redshift 10-ish. But the important point is this red line only goes to 0 after redshift 5 again. So as I said before, we really form stars from metal-free gas until redshift 5 in our simulation. And the next thing was to check where do those stars actually form in the galaxy. So this is checking the subhalo in which the stars are forming the metal-free star, like the stars for different populations. So the subhalo is then more or less the galaxy where they're forming. And the blue line shows you the top 1 star, the top 2 stars are the black line. Top 3 is above redshift 8 is the green one, and below redshift 8 is the red one. And so especially if you look for the more massive galaxies, you see, well, the top 1 starts to form in a bit more a larger subhalo. That's logical just because they form at later time, so at that point the galaxy was already more massive. The black line is a bit more to the left because they form a bit earlier time. But the interesting thing is if you look at the black and the red and the green line, they form in different subhalos. And if you check at the mass, to be found, they're around 10 to the 7, 10 to the 8 solar mass. And especially even if you look at the red line, so the more later formed metal-free stars, they actually form in even like slightly smaller halos. And if you check also not only subhalo mass, but the halo mass, we also see that, it's a bit large because not all of it is like in the central subhalo, but still they don't form in the main halo. And so if we actually trace back the formation history, we find that most of those POP3 stars form XC2. And if they form within the main halo, they form in very small satellites very close to the Zier radius. And at later time, even if they form XC2, we can find them in the galaxy because they are like in very small halos, just shortly out of the Zier radius, and then fall in at later time into the main halo. And then it also makes sense why after redshift 5, when our box is reionized, we don't form them anymore just because those small halos of 10⁷, they just ionize the full gas in there, and then they stop forming stars. So I come already to my summary. At least in our simulations, POP2 star formation starts to dominate between redshift 15 to 20, depending on the halo mass we look at. But we always find that metal-free stars are forming until the end of the epoch of reionization. They're typically forming in very small halos, like 10⁶ to 10⁸. And they're forming close to the Zier radius, so they form like XC2, or they form in very small satellites, which were just accreted into the main halo. And yeah, I mean, so we should be observable at redshift 5 to 6, we should still find some POP3 stars. And the THESAN-ZOOM is ideal for this study because on the one hand, we have self-consistent RT, including Lyman-Werner radiation. We have a resolved multi-phase ISM. We have molecular hydrogen chemistry, which we need like to cool down this metal-free gas. And we have dust physics also. And we have high resolution, so we can actually really resolve the structure in those very small mini halos, like 10⁶ to 10⁸ solar mass. Yeah, thanks a lot.
So Oliver, these very low metallicity stars, they often are argued to be massive because they formed out of larger clumps of gas. And if so, they are short-lived and they disappear. If they end up as black holes, or we don't, or if they just explode as parent stability supernova, we don't have them around anymore. So, but if the mass function goes down to solar mass stars, then we should still be able to see them in the Milky Way, right? And the question that was discussed for decades is whether they should be, because on the one hand, the galaxies from the inside out, so the core of the Milky Way might have old stars in it, but at the same time, we see globular clusters with very low metallicities, dwarf galaxies with in the halo. So you would expect to see them either in the halo of the Milky Way or in the center of the Milky Way. What do you see in the simulations? Where do they end up, these low metallicity stuff?
Well, so if they are like long-lived and slow mass, they would all be at the outside of the halo. So ideally, probably in small dwarf galaxies, like not in this main halo, or like at the outskirts. But they never form in the central galaxy. Like in our simulation, like only at the beginning, but after like redshift 15 or whatever, they don't form in the central galaxy anymore. But they all form. I think it's mostly like really at the edge, you form a mini halo, and then it gets accreted. So only accretion don't end up in the central halo. So it should be all in the outskirts.
Thank you. Questions, Daniel?
But so I'm trying to understand what edge means, because the edge of the halo at redshift 10 is only like 10 kiloparsecs visible distance, so it's right around the solar neighborhood today. So I'm just trying to understand, when you say ex situ, does it really mean ex situ today, or does it mean ex situ as the galaxy was at redshift of 4, say? So I think it would be interesting to actually get the radial profile of these, where these remnants actually would be.
Yeah, so when I say ex situ, it's like at the formation time, they were not part of the halo.
Yes.
But yes, I mean, I have some plots actually like measure like the stellar density as a function of like radius. Yeah. And you can see that the POP3 stars at redshift 3, they're all much more further out than POP1 and POP2 stars. But I don't have I have the in my paper. I can show you there.
One thing to keep in mind, the sun will become a white dwarf in 12 point. After an age of 12.3 billion years or so. That's a billion years or more, 1.5 billion years less than the age of the universe. So that means that POP3 stars forming before redshift 6 are all white dwarfs now if they had the solar mass. And the interesting question is also whether we can see them in the white dwarf luminosity function.
Really interesting. I was wondering what the total stellar mass of POP3 stars in your dwarf galaxies was. So the galaxies themselves are like 10⁷, 10⁸. But do you know how much mass is actually in POP3 stars, right?
I mean, the problem is, well, I mean, this is like at least a new stellar form mass. So if you go back to like, redshift 8, you're talking about 10% of the new form stellar mass would be POP3. And then like if you go down to redshift 5, it gets smaller.
So if it was 10% of 10 to the 8, you'd say 10 to the 7.
Yes, but like those small halos. But of course, that doesn't include like if the majority is still in the most massive stars, they explode and we don't have
Sure.
that, so.
Yeah. Because I work on POP research with James Webb, so maybe we can have a chat about
Oh yeah, sure.
Okay, let's thank Oliver again. Next, we will hear from Zili Shen from Yale. Not very far, a very competitive school with ours.
Hello, everyone. I'm Zili Shen. I'm a sixth-year PhD student from Yale, working with Peter Van Dokkum. And today I'm going to invite all of us to think about this peculiar population of galaxies called ultra-diffuse galaxies and how they can come to exist in our universe. So the image in the background here is a very deep HST image of one of the famous ultra-diffuse galaxies. And this is kind of how they look like. So they look like dwarf galaxies, but the reason they don't fit very well into the classic dichotomy of massive elliptical galaxies or dwarf galaxies is that they have very low stellar mass, but they have very extended physical sizes. So that means they are outliers on the galaxy mass size relation. So here I'm showing stellar mass on the x-axis, so dwarf galaxies to the left, massive galaxies to the right. And then on the y-axis is the effective radius in kiloparsec. So normally you would expect dwarf galaxies to be smaller and less massive, and then massive galaxies are on the upper right-hand corner. But by definition, ultra-diffuse galaxies are in the left corner of the plot. And that's because they have the stellar mass of dwarf galaxies, but by definition, their sizes are above 1.5 kiloparsec, so they're roughly the same size as the Milky Way, and they have very low surface brightness. So for theorists, think low surface density of stars. So they're very, very diffuse and puffy objects. And how could that come to be under lambda CDM and quote unquote normal galaxy formation? So these are the first two things that you might think of. The first one is it could be tidally interacting and tidally stretched. So we have all heard of dwarf galaxies falling into the Milky Way or some other gravitational potential. They can get stretched into streams. So then, of course, they become more diffuse and more stretched out. But not all ultra-diffuse galaxies are undergoing tidal disruption. And the second idea is that they might have high angular momentum. So they might be at the extreme tail of the galaxy angular momentum distribution. So that's also possible. I'm not going to talk about this very much because my observations don't really constrain the rotation of these galaxies. And then the other ideas about how you can get very diffuse dwarf galaxies have to do with something going on with their star formation. So one of the ideas is that you start with a massive halo with a Milky Way sized halo with its initial gas reservoir. And for some reason, the star formation is either quenched very early or is just extremely inefficient, like forming 1,000 times less stars than the Milky Way would have had normally. And then you can have a very diffuse low mass object inhibiting a Milky Way sized dark matter halo. And the other idea is that you can take a normal dwarf galaxy, so that's the dwarf galaxy with dwarf galaxy gas reservoir. And then if this dwarf galaxy has bursty star formation, so it had repeated starbursts and then gas outflows, and then all of that activity can kick up the dark matter and the stars and move them to larger radii in the galaxy. So then you can have a dwarf galaxy mass dark matter halo that's just been expanded due to this bursty star formation feedback. And then the stars that were formed would also be moved out to larger radii, and then that would lower the surface density. So this is the star formation feedback idea of how to make diffuse galaxies. So observationally, the star formation histories of these two scenarios would be very different, but we don't have great constraints on ultra-diffuse galaxies because they're so faint. So this is one of our attempts using the integrated light spectroscopy. So we took spectra of just all the light in these ultra-diffuse galaxies and tried to decompose them into different stellar populations and then see what the age distribution is. So these are from the light that we observe today. And these galaxies are ultra-diffuse galaxies from a sample that was discovered in the Dragonfly telescope. It's a new survey that we're leading. And then this paper that was submitted to the archive recently is the first description of the whole sample. So you can read more about them here. What I'm showing here, though, is just what we found about their stellar populations. So each panel is for a different galaxy, and then the age is showing the age of the stellar population. So to the left is the youngest population, and to the right is the oldest population. And then in the leftmost column, you see that those galaxies all have mostly old stellar populations, and they don't have any young stellar population. The middle column shows some UDGs have an old stellar population in addition to a roughly 1 gigayear-old stellar population. And then the right-hand column shows galaxies that just have stars of all different ages. So they maybe had an extended star formation history. And that would indicate that these galaxies on the right could be more consistent with the bursty star formation feedback model. And the galaxies on the left were quenched early and are more consistent with being in a cluster. And that is indeed what we find about the environment. So out of all the galaxies that we find that only have the old stellar population, 3 of them are in the cluster environment. And these are all the galaxies that we have that are in a cluster. All the rest of the sample are either in a group or in a field, so not in any massive clusters. And then this is where we see this extended star formation or a potential young population. So a caveat is that the method that we use is doesn't have extremely good time resolution. So if it indeed had multiple starbursts, we would not be able to resolve that because we're operating in this integrated light regime. So it's kind of difficult to tease out populations that are maybe 1 gigayear-old difference in age. But what we can say is something about like the presence of a young versus a very old population. So it seems like that this is consistent with the bursty star formation feedback idea of how you can make a dwarf more puffy, but that model would predict that these UDGs that were puffed up by stellar feedback would still have gas and possibly ongoing star formation today. So what if I told you that all of these galaxies in the field are quenched today? That's kind of surprising. And indeed, for my galaxies, I don't have H1 measurements, but there are some in the literature, field UDGs that don't have H1 gas or ongoing star formation. So that's kind of surprising because for normal dwarf galaxies, if you look at the gas fraction as a function of stellar mass, the low mass galaxies in the field should have a pretty high gas fraction of neutral hydrogen. So they should usually be blue and star forming and have gas. And indeed, there are some UDGs in the field, the 3 blue dots, they do have gas. But there are also some UDGs in the field that don't have H1 gas. And I'm showing HST images of 2 of them, DGSat1 above, and then this R1271 below. So these 2 galaxies don't have H1 detections. And if you look at their morphology, they look pretty consistent with just an old metal poor stellar population, kind of spheroidal, and then probably quenched early on. So how can these galaxies be both puffy and also quenched at current day? So my thinking is that you have to have potentially different explanations for the puffiness and the quench nature. So the previous explanations for why galaxies can be puffy either had something to do with star formation or environmental interactions. But to quench them, you definitely need either interaction with a cluster. So this is showing what's called a splashback galaxy. So even though it looks like it's in the field today, so that's the right-hand side of this plot, at some point in the past, it did fall into a massive galaxy cluster or galaxy group. And that's what quenched it and then led to, so these are snapshots from the simulation. And after the quenching by this past interaction, now it has an old stellar population that's just aging and becoming redder. And nowadays it looks like it's in the field, but that's really just because they left the Zier radius of the group. Or you could do it with interaction with the cosmic web. And this would mean that the gas was removed and it can still be far away from any galaxy clusters because it's interacting with something that we don't see. Cool, so that's my tidbit about the mystery of quenched UDGs in the field. They are puffy, they're quenched, and are they fundamentally different in the formation route or the type of object that they are in the field versus in the cluster? These are all questions that I'm still exploring. And here are the dragonfly cutouts from which we found these galaxies. So I'm visiting today and tomorrow. If you'd like to talk more, I'd be happy to meet with you. And that's my email. Thank you.
So Zili, you mentioned quenching, but in principle, it could be from supernovae or a central black hole, but you didn't bring this up. And so are the potential wells very deep for those galaxies? I mean, do we have any idea about dark matter?
That's a great question. If we knew about the dark matter halo, we could already distinguish between the failed Milky Way and the dwarf galaxy scenario. So we don't really know much about their halos.
There is no weak lensing or strong lensing.
Not that I'm aware of.
It would be nice to check. Razi, go ahead.
Yeah, wonderful. So if you go to the slide that they go from cluster to the actually to the field, I wonder, can you also check out their metallicity and just see there, because metallicity contains novel information about their formation history and things like that. So can you use an extra component just to see is this any bimodality in there, and then when was exactly the time of transition to the field?
We do measure the metallicity of these objects, but we just get one single measurement, and they're pretty low metallicity, like -1. So that's the measurement that we have. And then I don't know whether that could say anything about what time it potentially fell into cluster. Like these objects.
To the field.
Yeah, so these like young populations are very low mass component. So the galaxy is still dominated by the old metal pore component. Yes.
There was a question on this side then. Anyone? Alisa.
Thank you. This is really interesting. I'm just curious whether there are simulations that are good enough that could find analogs of these galaxies, and your idea about them passing through different things seems fascinating to me. And so I'm just interested if in these hypothetical simulations you could track the motion of the galaxy that is the analog backward in time, and how often that actually happens and how.
Yeah, there are some simulations that can make UDGs. I think they have to be like somewhat specifically designed to do this, because in cosmological simulations, there's just not enough resolution for this like dwarf and very low surface brightness things. I don't do any simulations, so I'm happy to like tell you what I know. But I'm aware that there are simulations that can make ultra-diffuse galaxies. Yeah.
And of course, if we had dynamics, we could constrain the properties of the nature of dark matter better than any. Yeah.
So if we observe the center of this kind of galaxy at the ratio 0.5 cluster, do you think they are still puffy or they are compact?
That's a good question. Yeah, it depends on which scenario they're going through. For the failed Milky Way scenario, they would already be kind of puffy. because they were probably quenched early on, if you think that given that they have all cell population that we observe today and they had to have been quenched at some point, then it would probably be already diffuse. Whereas the dwarf galaxies would be harder to say because then they would just have bursty star formation, and then how would you know they're the progenitors of today's ultra-diffuse galaxies? So, yeah.
Last question.
So for this, to distinguish between splashback and the feedback scenario, so these galaxies don't splash back too far, right? So I was wondering, can you find examples where there's like no cluster that could puff it up nearby? So that it must be something else?
Yeah, that's also a good question. I don't have a slide for this, but I can say that we looked at 2000 square degrees of dragonfly imaging and found all of the diffuse stuff. And then we got these spectra. So from everything that we saw in this large area, all of the ultra diffuse galaxies are within like 500 kiloparsecs of some massive host. So there's nothing that you would consider to be truly isolated. And this is still small number statistics. I mean, I have 11 galaxies, but maybe that's a hint that it's still consistent with the splashback idea, because to date, we actually haven't found a truly isolated quenched THG.
Thank you so much. Next speaker is Anya Nugent, incoming postdoc.
Okay. Hi, everyone. My name is Anya Nugent, and I'm a new postdoc here. To give a brief introduction to myself, I just graduated from Northwestern, where I was a member of Wenpei Fong's group, and my research focuses on observational studies of host galaxies of various astrophysical transients. The majority of my PhD thesis was focused on short gamma ray burst host galaxies. So for today, I thought I would talk about a paper that should hopefully be submitted very soon. This is still preliminary work, so it might change a little bit by the time I submit, but this has to do all about our process and neutron star mergers. So one question that many of us are trying to go after right now is, what are the astrophysical sites of our process elements? So what even are our process elements? Well, these comprise some of the heaviest elements on the periodic table, and notably include things like gold, platinum, and uranium, which are very abundant here on Earth. So figuring out where in the universe these elements are produced can help us better understand how we and Earth came to be. So there are two main proposed sites for our process, and these include neutron star mergers and the collapse of massive stars, or collapsars. So currently, neutron star mergers are the only confirmed site of our process. And this is because gravitational wave event 17017, which was the first binary neutron star merger to be detected by LIGO, was coincident with an R process kilonovae. Now, several short gamma ray bursts, which we also know are coming from neutron star mergers because of a coincidence of 17817 with a short GRB, have also been followed by probable photometric detections of kilonova, which kind of boosts this claim as well. Now, that obviously means that there's still no observational evidence that collapsars can produce our process elements. However, there's a lot of very solid theoretical work that shows that they not only can produce our process, but they may also be a major contributor of our process within our universe. Now, what's interesting about both of these sites is that neutron star mergers and collapsars have very different host environments and timescales, meaning the time it would take for each of these events to enrich an environment with our process, and even the kinds of environments they're capable of enriching are going to be very different. So for example, collapsars are almost exclusively found in very actively star-forming galaxies and have very short timescales of about 10 million years. Whereas neutron star mergers have a breadth of possible host environments, from star forming to quiescent galaxies, which we've observed with our short GRB population, and occur on more delayed timescales of about 10 to 200 million years. So another cool thing is that we've actually been able to observe our process in the absence of actually observing the event that produced them. So our process elements have been discovered in a variety of local group dwarf galaxies and galactic metal poor stars. And I'm bringing up one very notable example here, which is Reticulum 2. This is a local group ultra faint dwarf galaxy. It only has about 10 to the 4 solar masses, and 75% of the stars within Reticulum 2 show our process enhancement. Now, this means that an R process event had to have happened before all those stars were formed, so the R process made it into the star forming gas and those stars were born with that enhancement. Now, only about 1 in every 10 ultra-faint dwarfs show any kind of R process enhancement, suggesting that R process events in general are very rare, much rarer than our normal core collapse supernovae. So what's interesting is that we can actually take those event rates from our ultra-faint dwarf population and galactic metal core stars, and the abundances of R process that we see in those stars to get an estimate for how much R process there might be in the universe. And that's kind of what this plot over here is showing. Now, there's a lot going on in this plot, and I can't go into it in great detail, so I'm just going to point out a few important things. But what we've seen is that the R process mass estimates derived from our ultra-faint dwarf galaxy population and their event rates seem to match well with those of the observed neutron star merger population, suggesting that all of our R process from our neutron star mergers is making it back into stars. Now, that's kind of a problematic assumption because losses might actually be important, i.e. there might be cases where some R process is getting lost in the IGM or CGM and not actually making it back into stars. Now, this is really important to consider as this might help us understand how much neutron star mergers are actually contributing to the environments that we can detect R process in. So why are losses important? Well, for one, we know that neutron star mergers occur in galaxies with very little or even no ongoing star formation, meaning that there's very little star-forming gas left to enrich. And a prime example of this would be 170817, which occurred in a very red and dead quiescent galaxy. Now, on top of this, about 15% of our short GRBs are also occurring in galaxies with no more active star or no star formation left in it, suggesting that the population of neutron star mergers occurring in galaxies with no more star formation is actually pretty significant. Now, on top of this, we expect that merging neutron star systems will be traveling at very high systemic velocities, meaning that when those systems actually merge together, they can occur very offset from their host galaxies. Now, if we have our R process being synthesized well outside of the galaxy, that might mean that it takes a really long time for the R process to make it back and mix with the star-forming gas. And if that time scale is longer than the active star formation period of the galaxy, that might mean that no stars are capable of being enriched. So our goals for this paper was to quantify the timescale for our process to travel from a neutron star merger location back into the star-forming gas and enrich that environment, and determine the fraction of stellar mass that's capable of being enriched from a single event to kind of start to quantify how important these losses might be. And we're using our short GRB population to do all of this. So I'll start off by quickly describing how we quantify our enrichment timescale, or the time for the R process to travel back into the galaxy. So we consider two different scenarios. And in the first scenario, we assume that our neutron star merger has occurred somewhere out in the halo of the galaxy. Now, as gravity from the galaxy will try to pull the R process down, the hot halo gas surrounding the R process can keep it in a quasi-static equilibrium. So we actually have to wait for that gas to cool for the R process to fall back. So the timescale in this scenario for the enrichment timescale is going to be roughly the cooling timescale. Now, in our second scenario, we assume that the neutron star merger has occurred much closer to the galaxy. And in this case, it's going to be turbulent diffusion processes that are created by stellar winds, galactic inflows and outflows, and supernovae that are going to kind of scatter the R process around the galaxy. And the timescale for this to occur will be roughly the diffusion timescale. Now, we have actually verified that diffusion is going to be more efficient at moving R process around at very low galactocentric offsets, whereas cooling will be more efficient when the R process is synthesized very far away from the galaxy. So this shows our main results for our enrichment timescales. I'm showing you them in comparison to the neutron star merger galactocentric offset and the host galaxy halo mass. Stars here represent the GRBs that had kilonova associated with them, and the circles are just the rest of the short GRB population. So what you'll see here is that the majority of our enrichment timescales are over 10 million years, with the grand majority even being over 200 million years. So if we think back to those minimum merger timescales that I was talking about before, this means that the enrichment timescale is at least on order of the minimum time it takes for a neutron star system to merge together. So that would imply that our process enrichment from neutron star mergers is not instantaneous, that there is actually a delay between when a neutron star merger occurs and when an environment is actually capable of it being enriched. Now, because of this is such a long delay, that may also mean that some of that R process is getting lost in the process and not actually making it back into star-forming gas. So the other thing that we wanted to do was determine what are the important factors that determine the degree of enrichment. So we actually have star formation histories for all of our short GRB host galaxies. And what we did was we evolved those star formation histories from the redshift of the GRB out to redshift 0, assuming a constant star formation rate, and determined the amount of stellar mass that was formed after the R process had fallen back into the galaxy to determine the fraction of enriched stellar mass. And then we compared that fraction of enriched stellar mass to various properties of the host galaxy, like the amount of stellar mass, the amount of active star formation, and even the offset of that short GRB. And what we found was most significant was this degree of enrichment seems to trend more highly with the amount of active star formation within the host galaxy. Now, this also suggests that if a galaxy doesn't have any star formation left, that there's really no chance that that environment will be capable of being enriched. So if not every environment is capable of them being enriched, that means that losses are in fact important. And I think going forward, when we're considering how much neutron star mergers could be contributing to the chemical enrichment of our universe, we need to be considering losses. And this is going to be especially important for determining if we do indeed need another R process channel to explain all of the observed abundances that we can detect in the universe, and especially a prompt channel like collapsars. So thank you very much.
Thank you, Anya. Perfect on time. Some people argue that gold, platinum, and uranium are the sources of all evil on Earth. So the question is, how unusual is it if you were to select stars within the Milky Way galaxy? Is the sun unusual, or I mean, is there an island much more enrichment that we are not part of, or is it sort of typical, roughly the same everywhere in the Milky Way? Do we know?
Yeah. I would say error bars are very high. So this is showing like all of the different R process detections we have. So we have our ultra faint dwarf galaxies, which I showed before. These are deep sea floor plutonium abundances. And then I think this is the sun, and then the EMP, those are our galactic metal poor stars. And so you can see uncertainties are very large for all of these things. So I would say it's hard to say if we're rare in comparison to others.
From your models, you would expect most stars in the Milky Way to be similar to the sun, or do you expect islands of our process?
I think that would have to do with like when an R process event occurred and when the stars were formed, like if it happened before a star formation burst. So there could be islands if there was a gap, like a large gap in between a star formation period in a galaxy.
Thank you. Please.
Really nice talk. I had no idea that they were so offset a lot of the time. Well, I'm kind of wondering what kind of energy is injected in these kilonovae, because I work on the circumgalactic medium to some degree, and it's kind of interesting if you're going to start detonating supernovae level events.
Yeah.
Offset 10 kiloparsecs from the galaxy,
yeah,
you'll be detonating them in a much more diffuse medium, which will blow stuff much further than we typically would include in models.
Yeah.
So kind of, yeah.
Oh, like, so we did actually look like how far like the kilonova can spread, and it's only about 10 parsecs. It's not going to move very far. Yeah.
And this is a small subset of all explosions. Sure. So in terms of energy output, the regular core collapse probably dominate. Yeah. Questions? Yeah.
Do you see any correlation between delay time and star formation activity? Because one of the processes will be like fountain or like outflows that can change the deposit time, right?
Delay time and the star. So we haven't calculated individual delay times for all of our short GRBs. We have looked at delay times, which we obtain from the star formation histories of the host galaxies. And obviously, if a galaxy is more quenched and quiescent, we assume in that case that the delay time would be longer because the stars formed a longer time ago.
Okay. In simulations, the time scale of gas coming back from the halo is actually similar to what you get like
Oh,
500.
okay. Oh, okay, yeah, we haven't looked at that, but that might be interesting to do in the future.
It would be nice to put it in the simulation. Okay, any other questions, comments? Thank you so much, Anya.
So I'm going to talk about turbulence in the molecular ISM. And the question that I'm going to address is, if the ISM is turbulent, why do observations of molecular clouds show evidence of hydrostatic and virial equilibrium? So I put up 3 surveys, the first one is the older UMass Stony Brook survey of the center of the galaxy. Middle one is the Galactic Ring survey. This one is the Thaddeus Dame survey. And the straight lines in all of the figures are the equation of virial equilibrium, where twice the kinetic energy equals the gravitational energy. So the more recent surveys show that molecular clouds have an excess of kinetic energy, which could, so they could be brought into virial equilibrium with an external confining pressure. And the earlier one, clouds seem to lie on line of virial equilibrium, probably due to a inaccurate calibration of the CO column density to the H2 mass of the cloud. So the problem is right now there are no numerical simulations of the turbulent molecular ISM that produce clouds that are in hydrostatic or virial equilibrium. And not only is this interpretation of virial equilibrium strongly denied, but sometimes also the data. I'll get to the hydrostatic equilibrium in a moment. So it seems like the theoreticians and the observers are kind of stuck in this Marx Brothers movie, Duck Soup, where Chico Marx says, well, who are you going to believe, me or your own eyes? And the reasons given for ignoring observations, they say molecular clouds don't exist. And you say, well, yeah, if you go back to the sort of age of dinosaurs, 1980s version of the molecular cloud, which is isolated object with an internal balance of energy and some boundary, so yeah, that could be true. But so that's an argument based on the logical fallacy of the false premise. You say, well, you're saying that molecular clouds are this way. So properly stated, you say molecular cloud is a region of high density within the turbulence, high column density. The other reason is cloud boundaries are a false construct. Observers, let's start, say molecular clouds don't really have a sharp boundary. There's not a phase transition. Observers generally pick a boundary based on the observational sensitivity, whether they set it up. So the observational sensitivity does give more or less a boundary. But ignoring the boundaries, molecular clouds have a characteristic length scale. The other argument against this confinement by an external pressure is that thermal pressure is microscopic and isotropic, and turbulence cannot act like a thermal pressure as well. It doesn't have to. What we're talking about in virial equilibrium is energies averaged over volume. So we think about the pressure, we should think about the pressure as the turbulent pressure energy per unit mass, in which case this pressure energy has the same definition as the kinetic energy, turbulent kinetic energy, just the velocity dispersion squared. Also, arguments are that virial equilibrium is a misinterpretation of energy equipartition. Part of the -2 profiles are ambiguous, they could be various things. But the problem is you can't just think about the energetics. If you're going to propose an alternative, it has to be one that doesn't contradict all the other observational evidence that we have. So one of the first alternatives was proposed by the Caltech theoreticians, Peter Goldreich and John Kwan. They pointed out in free fall collapse that the kinetic energies, the gravitational energies would come into equipartition And the density profile will be approximately R-2, but that was shot down instantaneously by a pair of observers, Ben Zuckerman and Yale University, who said, well, if you did that, the star formation rate in the galaxy would be orders of magnitude higher than it's observed to be. So I'm going to take this definition of molecular clouds in orange and apply it to observation data and solve the problem. So the data set that I'm using is the 5-college radio astronomy Boston University Galactic Ring Survey. It's 13 CO spectra over 75 square degrees in the center of the galaxy. So it's complete. It's not just molecular clouds. It's a complete survey. It's Nyquist sampling, which is important because you're not missing any of the spatial frequencies due to the sampling. And there's 6,000 clouds identified, not with the method that I'm going to use, but there's plenty of clouds to choose from. So just to look at the data, so this is what the data looks like, right? So on the left is the 13 CO integrated intensity, and on the right is the 13 CO line width. So there is a molecular cloud. It has a characteristic length scale. And you can see from the plot on the right that if you can measure a 13 CO line width, then it's molecular out to several times whatever you choose as the characteristic size of the cloud. There's also an anti-correlation of the column density and the line width. So this means that there is a higher turbulent pressure energy per unit mass outside the cloud. And this external confining pressure then derives from molecular ISM around the clouds. All right, so this is how I define a molecular cloud. So you find a peak in the 13 CO emission that has a half power point in the azimuthally averaged emission. So it has to have a half power point so it can have a characteristic size, and it's not just some random fluctuation from the noise. So what I've done here is for clouds of 3 different lengths, I've scaled all the clouds to a non-dimensional brightness of 1 and scaled their length scales to non-dimensional units of the half width, half max. So the dotted line is the half width, half max, and the dashed line is what I'm going to call the characteristic size of the cloud. So this relates back to how we describe an exponential in physics. We say that there's a regime that's linear where we can approximate exponential by linear compared to a steeply rising section in the center. So the red curve is the column density from the Lane-Emden solution for hydrostatic equilibrium. So these are consistent with perturbed versions of hydrostatic equilibrium. And then to get the external pressure, I can measure the line width just outside of my characteristic radius of 2 half width, half max. So these are a little noisy, so I can stack all 4,000 clouds. And on the left, this is showing the line width in non-dimensional units, and the right is showing the column density. So you see that the line width rises from the center of the clouds, goes up about 40%. Half of that increase occurs inside the cloud. Now, on the right, the red curve is the observed column density profile. And there's 2 solutions of column density with the Lane-Emden equation. The first is the dotted line, which is for a constant non-dimensional temperature, and the dashed line is non-dimensional temperature that is proportional to the square of the line width. So that's the turbulent energy. All right, so that's hydrostatic equilibrium. Here's virial equilibrium. So this plot is similar to the ones that I showed at the beginning, except I'm plotting it on the vertical axis is kinetic energy in per unit mass, and horizontal axis is the gravitational energy. So those are in real units. And this is a histogram of all the clouds in this 2-dimensional space. So what I do is I fit a elliptical distribution to the clouds, find the mean and the standard deviations in both directions. And then a line of constant pressure through the mean, then this is what's required for the average of all the clouds, then is in standard units per volume is 2 times 10 to the 4 Kelvin per centimeter cube. So that happens to be the pressure of the multi-phase interstellar medium at the galactic midpoint, according to some estimates. Then the other thing to notice is that sorry. So anyway, going across is the so the dashed line is 0 pressure. So going across is the lines of constant pressure. There's 3 orders of magnitude in the external pressure clouds. So just say jumping ahead, what you want to do is think about what this means for the turbulence, not what this means for the clouds. Now this is what it means. So when we make the multi-scale average of column density, we have average clouds of all sizes, scales. So this multi-scale average is hydrostatic equilibrium across all the spatial scales. That's consistent with the low rate of star formation of the galaxy. And the time scale is of the turbulence is the crossing time. So it's R over velocity dispersion. So this means that the multi-scale average is also an average over time scales. So therefore, the hydrostatic equilibrium is a stationary property of the turbulence, and departures from the hydrostatic equilibrium are the fluctuating turbulence. And the molecular clouds are in high density regions. So the interpretation of Zier equilibrium, so we have these different time scales. So if I write the Zier equilibrium equation in 3 terms, time dependent, so there's kinetic energy, gravitational energy, external pressure. Now, these are varying on 2 different time scales. So the cloud scale separates smaller regions inside the cloud from larger regions outside with their corresponding shorter and longer time scales. So then I can say, I can treat this external pressure, this P up here, parametrically, and can hold that constant. And I say, this allows the clouds to evolve to virial equilibrium within this time scale. So that's how long virial equilibrium lasts. And in a snapshot in time, the clouds appear to be in virial equilibrium. Right. The other thing to notice here is that going back to this plot, so the straight line is a solution for combinations of kinetic energy and gravitational energy that give you virial equilibrium, and crosswise is different pressures. So the elliptical distribution tells you that there are more clouds at virial equilibrium than out. So population lifetime argument says that the virialization time scale is shorter. This is the last slide. Sorry about that. All right, so these are the observed properties of the interstellar medium. So I said, well, why is this a new explanation of turbulence? So, understanding might be premature and a bit optimistic, but the observational data are explainable within a theoretical framework of turbulence. So a successful model of turbulence will be able to reproduce these observations.
Okay, Larry, we are over time, and will not be time to ask questions.
You got 2 more minutes. You didn't start till.
Well, one interesting point is there couldn't be dark matter in those clouds because you get a good consistency with, right? So the mass that you infer is the mass that you see.
Yeah, I don't think the scale of the clouds are enough. They're too small to be much affected by dark matter.
Well, it depends on the nature of dark
Depends on
matter,
the distribution of dark
but it's
matter,
good to know that the baryons can account for what you see.
Yeah.
Yeah, because there are modified theories of gravity, and you might, anyway. Yes, Alisa.
I generally agree with you, Eric, but I just have one very specific question. In the very first set of Larson-like plots where you had the dinosaur, why did you say that it's something wrong with the CO calibration instead of just saying that external pressure isn't accounted for properly?
Oh, it's just, in that 1987 survey, it's kind of complicated. So the answer is, Mark Heyer discusses this in several pages in his 2009 paper. But that plot is in kind of unusual units. So that's what it seems to be. So let me, if I can go back to that very quickly.
Well, Pat Thaddeus's calibration would have given a different answer.
Right. So
And
this.
Pat Thaddeus was here.
I wish. Right. So these clouds in the circles are a subset of those clouds there that were recalibrated by Mark Heyer. These are the galactic ring survey clouds in the solid. So that's the answer to the question.
Of course, Elisa, you did your
We'll discuss
PhD at
this
that time
later.
and
We'll talk about it later.
you know it quite well. Anyway, we'll leave this for after, so thank you all for joining us.